In this video, I'm going to take a look at Euclidean geometry, but with a focus on ratios, proportionalities, similarities, and applying it to these kinds of questions. Now, this question is from the GAUTENG 2025 trial exam. Question 10.2 reads, in the diagram below, A, C, and F are points on a semicircle with center B. A circle with center C is drawn. The radius of the semicircle is twice the radius of circle C. FED is a tangent to both circles at F and E respectively. ABCD is a straight line. And so the first question reads, prove that triangle AFC, so let's highlight that. So AFC is this big triangle here. So prove that that triangle is similar to triangle FEC. So triangle FEC is this smaller triangle here. Now, how do we do that? So one way we could approach it is by examining the question that they are asking us to, examine what they are asking us to do. So if I had to write this out, triangle AFC similar to triangle FEC. In AFC, F is specifically angle F2 and C is specifically C1. Then in triangle FEC, F is F3, E is E1, and C is C2. And from here, what we do is we can say, or try to figure out, work backwards, why would angle A equal angle F3? So in other words, why is this angle equal to that angle? Then we ask ourselves the question, why is angle F2 equal to angle E1? So why is this angle going to equal this angle? And then lastly, why is angle C1 going to equal angle C2? So why is this going to equal that? And perhaps looking at it this way, for some of you, may make it a bit easier. So since we know that the line FED is a tangent, we can see that F3 is an angle that is made from a tangent to a chord. So angle F3 is going to equal angle A because of the tan chord theorem. So we can write statement, reason. We can say that angle F3 is going to equal angle A, and that is because of the tan chord theorem. So that's been taken care of. So F3 and A. Next, let's shift our attention to F2 and E1. So why is E1 equal to F2? Well, if I look at the smaller circle, CE is the radius, because C is the center. And we know that FED is a tangent. And so the angle that the radius makes with the tangent is 90 degrees. So E1 is equal to 90 degrees. And that is because the radius is perpendicular to the tangent. Now we just need to figure out why F2 would be 90 degrees. Well, since we know AC is a semicircle, well, we have a semicircle. F2 is going to be 90 degrees because it's angles in a semicircle. So F2 is equal to 90 degrees, angles in a semicircle. And then that must mean that C1, or rather C2, is going to equal C1. And that's some angles in a triangle. Now let's just make sure that we've shown the correct things. We have F3, E1, and C2, so that's one triangle. We have A, we have F2, we have C1, that's our other triangle. We've shown that those angles are equal, and therefore we can conclude that triangle AFC is similar to triangle FEC. And the reason is angle, angle, angle. Now let's take a look at the next part of the question, which says, if the radius of the smallest circle is P, determine the following in terms of P. Okay, so let's input that information right here. So clear this. So if this is P, they want us to figure out what FC is. So FC is this line here. Now FC is common to both those circles that both those triangles that we just proved. Okay? So what we can do now is let's go back to the information that was given. They tell us that a circle with center C is drawn. The radius of the semicircle is twice the radius of circle C. So the radius BC is going to be double P, so 2P. That means AB is also 2P, which means that AC is going to be 2P plus 2P, which is 4P. Now we can use the proportionality that we just, or similarity, to get ratios and solve for FC. So what we can do is we can say that AC, since we have that side, so AC divided by FC is going to equal EC, since we have EC and FC, it's going to be FC divided by EC. All I did was I looked at our triangle similarity and I chose sides that we know or that we want. We know AC and we know EC. We wanted FC, so that's why I chose those. Now we know AC is 4P, FC is what we want, that's equal to FC, which is what we want, divided by EC, which is P. Now let's cross multiply. 4P times 4P times P is equal to FC times FC. 4P squared is equal to FC squared. Then we can say that the square root of FC squared is equal to the square root of 4P squared. That means FC is equal to 2P. Now let's take a look at this next question, which reads, calculate the length of FD if it is given that FE is equal to ED. So we worked out the length of FC, let's put that there. And they want to know what is the length of FD if FE is equal to ED. Well, what we can do here is if we focus on this yellow triangle, we know that E1 is 90 degrees. So we can use Pythagoras to solve for FE. And if we know what FE is, then we know what ED is, then we can solve for FD. So I can simply say that 2P is my hypotenuse. FC is the hypotenuse. It is the side that is opposite the 90 degrees. So 2P squared plus, 2P squared is equal to P squared plus FE squared. Then 2P squared minus P squared is equal to FE squared. And this is because of Pythagoras. Let's write that in. P squared is equal to FE squared, which means that FE is equal to the square root of p squared. So FE is equal to P. So if FE is P, then ED is P. Therefore, we can say that FD is going to equal P plus P, which is 2P. Now question 11 reads, in the diagram below, cyclic quadrilateral EFGH is drawn. Chords EH and FG are produced to meet at K. M is a midpoint on EF such that MG is parallel to EK. Further, KG is equal to EF. Now I'm going to highlight KG and EF, just so it's clear to us. Now question 11.1 reads, prove that EF squared is equal to KE times GH. So first thing I want to do is I need to figure out what triangle these are going to be part of. So I'm going to write EF squared as EF times EF, and that's going to equal KE times GH. Next, I'm just going to simply switch them around. So I'm going to take this EF, bring it to the denominator, and I'll take the KE and move it there. So I'm going to have EF over KE is going to equal GH over EF. Now it's just a matter of checking if these triangles exist. So the first one is EFK. Does that triangle exist? So I'll use a different color here. EFK. Yes, that triangle does exist. So I can move on to the other part, the other side of the equal sign. So here we're looking at GHEF. That is not a triangle. That does not exist. However, we know that EF is equal to KG. So maybe we could replace this and instead say GH over KG. Does that now make a triangle? Let's see. So here we're going to have GHK. Is that a triangle? And we can see here GHK is a triangle, and so we are on the right track. So now what we need to do is we need to focus or zone in on those two triangles. So we're going to say in triangle EFK and triangle GHK, we need to figure out what's going to be equal and why are they going to be similar. Once we've proven that they are similar, then we can prove our expression. So we can see here, so here, since this is a cyclic quad, since EHFG is a cyclic quad, then G1 is going to equal angle E. So we can say here that angle G1 equals angle E. And that's because the exterior angle of a cyclic quad is equal to the interior opposite. Then we can say the same thing for H1. We can say that H1 is equal to angle F. And that's again exterior angle of a cyclic quad. So then that must mean that, well, angle K is common, so we've basically proven it. So we can simply say that triangle GHK is similar to triangle EFK. And the reason is going to be angle, angle, angle. Now it's not too neat, so let me just neaten this up a little bit. We got that and that. Okay, now we can go ahead and prove the equation that they asked us to do. So we can say that EF over GH is going to equal, they want KE, so EK over GK. Now let's switch it around. We got EF times GK is equal to EK times GH. Now we know that GK is equal to EF, so it's going to be EF times EF is equal to EK times GH. Therefore, EF squared is equal to EK times GH. And we've now proven it. All right, now let's take a look at the next question. So the next question says, prove that kg squared is equal to EM times KF. So what we can do here is, if we focus in on this big triangle right here, because these lines in green are parallel, it means that the sides of those triangles are going to be proportional. So we can say that EF, so this entire side, divided by EM is going to be equal to KF divided by KG. So EF divided by EM is going to equal KF divided by KG. Now I can switch this around. Well, the reason here would be the proportionality theorem. Then I can switch this and this. I'm going to get KG times EF is equal to KF times EM. But again, we know that KG is equal to EF. So KG times KG is equal to KF multiplied by EM. Now we can get our concluding statement, KG squared is equal to EM multiplied by KF. And we have proven it. Okay, now let's move on to the last question here. The last question reads, if it is given that KE is equal to 20 units, so KE, this right here, if that is 20 units, KF is 16 units, so KF is this entire side here, that is 16 units, and GH is 4 units, so GH, this side here, is 4 units. Calculate the length of EM. So they want us to calculate this side right here. Now, we've already figured out that, or they've already told us that EF is equal to KG, right? So if EF is equal to KG, what we can then do is, since we have expressions for EF squared and KG squared, let's square both sides and then replace it. So EF squared is going to equal KG squared. But EF squared is equal to KE times GH. And KG squared is equal to EM times KF. And now let's substitute what we know. Well, we know KE is 20, so that's 20. GH is 4. And that's equal to EM, which is what we want, multiplied by KF, which is 16. So 20 times 4 divided by 16 is going to equal to EM. And EM is therefore equal to 5 units. This question reads, in the diagram below, two circles touch internally at A. AB is the diameter of the large circle. AL is the diameter of the small circle. S and L are the centers of the circles. D is the point on the small circle and C is the point on the large circle. ADC is a straight line. M is a midpoint on LB such that MN is parallel to LC. Question 9.1 reads, prove that DL is parallel to CB. So DL is this line here and CB is that line right there. So to prove this, I'm going to focus first on the small circle. So 9.1, I'm going to say that angle ADL is going to equal to 90 degrees. Because since AL is the diameter of the circle, this angle is going to be 90 degrees. The reason is going to be angles in a semicircle. Then likewise, I can say that angle ACB is also going to equal to 90 degrees because of angles in a semicircle again. Now, obviously then focusing on the larger circle. And therefore, since they both equal to 90 degrees, we can then conclude that line DL is going to be parallel to line CB, and because of they are going to be corresponding angles. Now question 9.2, prove that 2SD is equal to LC. Okay, so I'm going to highlight this. So LC and SD. Okay, so since L is the center of the larger circle, LC becomes the radius. So LC is going to equal to LA, right? Because they're radii. But LA is equal to the diameter of the small circle. Now, the radius of the small circle is SD. So LA is going to be 2 times SD. So therefore, I can then equate these two. I can say that LC is equal to 2SD. Done. Now, question 9.3. Determine the value of SL over AB. So let's clear this up. SL is going to be this over AB, which is going to be that entire line. Okay. Let's call SL X. That means AS is going to be X, which means that the radius of the large circle is going to be 2x. That means that LB is also going to be 2x. That means the diameter AB is going to be 4x. So SL over AB is going to be x over 4x, which then simplifies to 1 over 4. Question 10. In the diagram below, triangle PQT is drawn. O is the center of the circle and OD bisects PQ. PT is perpendicular to QT. Prove the following. 10.1, O3 is equal to QPT. So I'm going to highlight that. They want us to show that this angle here is equal to this angle here. So to prove this, the first thing I'm going to do is I'm going to say that D2 and D1 are going to be 90 degrees. So D1 is going to equal D2, which is going to equal 90 degrees. And that's because the line through the center to the midpoint of a chord will bisect the chord, which we can see PD is equal to PQ. It bisects the chord and it is perpendicular. okay? So then that means that PDOT is a cyclic quad. That's because since D1 and angle T are 90 degrees, those are opposite angles and they are supplementary. So the opposite angles are supplementary. That makes O3 the exterior angle of a cyclic quad. So that means that O3 is going to equal QPT because it is the exterior angle of a cyclic quad. Now question 10.2. Prove that triangle OPD, let's highlight it. So OPD, I can see it here. OPD. So that one is going to be similar to QPT. Let's highlight that. QPT is this one here in blue. Okay, not a problem. Let's do that. So we know that D1 is equal to T, which is equal to 90 degrees. And we've proven that already. Then we know that OP is going to equal OQ. Well, OPs will equal to OQ because they are radii. Next, we can say that P1 is going to equal, let's use a double line here. P1 is then going to equal angle Q. And that's because they are angles opposite equal sides. And then therefore the last angle is going to be O2 must then equal QPT, which is basically P1. No, QPT, that's not P1. Let's go back. D1, so that's done, that's done. P1 is equal to that. Then that means, yeah, O2 is equal to QPT. Some angles in a triangle. And therefore we can say that triangle OPD is similar to triangle PQT. And reason is angle, angle, angle. Now the last question, question 10.3. Prove that OQ times QT is equal to PD squared. Okay, so let's start with our triangle proportionality that we just used. So, or that we just proved. Since these triangles are proportional, or since they are similar, the sides will be in proportion. So we can say that OP divided by PQ, so OP divided by PQ is going to equal PD, so this here, divided by QT. So PD divided by QT. And that's because sides, or rather, instead we can say triangle OPD similar to triangle PQT. Next, we can write, or we can cross multiply. We can say that OP times QT is equal to PD times PQ. So we have the OQ. No, we don't have the OQ. Well, OP and OQ are equal. So OP and OQ are equal. So we can say since OP is equal to OQ, I can say OQ times QT is equal to PD times PQ. Right? So we've gotten this this left hand side done. Okay, now we need to take a look at the right hand side, so PD and PQ. So let's take a look at PD and PQ. Well, PQ, if I call PDX, then PQ is going to equal 2x, because they tell us that that they are equal. They tell us that PD is equal to DQ. So instead of writing PQ, I can write 2PD. And this is because PQ is equal to PD. So that's going to be PD, that's going to be OQ, that's going to be QT. And now I've basically got our answer. So OQ times QT is equal to 2PD squared. Done.